everyone. My name is Ceri. I am a physicist here working with the Science and Technology Facilities Council. I'm based here at the Rutherford Atherton Lab, and I've been here for quite a few years now. I've actually been on site for over 8 years in total, but I first came here the summer after finishing my undergraduate degree at Oxford, just up the road. I've been here in many different forms, so I started off as a PhD student, and then 4 years ago I started here as a staff scientist, and I've been involved in lots of cool stuff ever since. I'm going to give you a little whirlwind through the type of science and research that I do, but also give you a bit of an idea of how that links to innovation and what I mean by innovation. Where does the next generation of technology come from? And I hope that you'll see that actually some of the laser science that we do here has a big part to play in innovation and driving really interesting and new technology. So I work for the Central Laser Facility. That's one of the departments that we have on site here, and as the name suggests, it has a whole bunch of lasers that do all sorts of science and research, from the life sciences and medical research, biology and chemistry, right through to high energy density physics and plasma physics, which is more in the realm of stuff that CERN is used to. But essentially we do a whole bunch of science and research, but we also do a lot of technology development. So we do a lot of in-house stuff that's to do with the next generation of lasers. How can we make lasers better? What else can we do with them? So first of all, talking of lasers and innovation and technology, it's quite a usual thing now to say that lasers are in the background of everyday technology, literally in all different sectors, all different markets, from communications right through to manufacturing and steel cutting to medicine. That's one thing people always say that lasers are really great for is medical applications, but there's a whole bunch of cool stuff they do, from measuring distances between here and the moon to simply making fantastic light shows. So yeah, lasers are really versatile. They're a versatile technological wonder, which is how I normally describe them. But I think I have a huge respect for this invention, and so I hope to do that justice in the science and research that I do with lasers. A little story just to get us going, talking about innovation. One of the really cool and newest innovation stories that have come out from the Central Laser Facility in the last few years is something called spatially offset Raman spectroscopy, or SORS for short. Now, I don't have time to go into what that is, so Google it. There's plenty of explanations on Google. But the key thing behind what SORS can do is that it can get a chemical fingerprint of something that's within an opaque container. Now, this process was developed in the lab purely for explorative purpose. They were actually looking to see if they could use this process to look for fingerprints of bone disease beneath the skin. So they wanted to be able to do this without having to physically take a bit of bone sample and take it to the lab. They wanted to just use a laser to look through the skin. So the technique was developed a couple of 100 meters away from here at the CLF, patented in 2004, and then a company was formed in 2008. That is now what was called Cobalt Light Systems. Their first product wasn't to do with clinical or medical applications, it was actually to do with security. Because in 2001 there was a big security issue, and from then, especially in airports, we've been limited in how much liquid we can take on board with us on flights. So they actually applied this technique to say that we could look inside sealed bottles and sealed containers, and we can tell you in 10 seconds or less, likely less, whether that stuff in that liquid is dangerous or not. So to develop this company called Cobalt Light Systems, and this product now, this box, sits about that high. It's in 60 airports across Europe. It's definitely in Heathrow and Gatwick and Glasgow, because I've seen them recently. So next time we're going through the security gates, look out for a box with a grey box with a red door. That's the invention that came out of the Central Laser Facility, and that's one of the products and one of the reasons why it will be very soon that 100 milliliter limit on liquids that we can carry on flights and planes will be lifted because of this technology. They are a real company now. They have more than 40 employees. they have a huge product range. So they're doing this for pharmaceutical applications as well as security applications, and actually just in some cases health and safety inspections. So they've got a huge product range. They're getting awards all over the place for innovation and enterprise and engineering and exports as well. So this is a huge economic success as well for our countries is to have really great inventions and then actually see reaping the rewards of that for a few years later. You can see there's a decade in between that kind of start and celebratory success. It takes a little while, but it gets there in the end. I'm really inspired by that journey. But actually the lasers that I use are not the kind of lasers that you do spectroscopy with. In fact, the lasers that I work with will never be able to fit them in a box this size because I work with the most powerful lasers in the world. And just to put that in perspective, when you're talking about lasers and light and photons, we often talk about either power, which is how I just described it, or intensity. So simply how we measure the energy delivered at a certain time over a certain area. Now, the light intensity that you feel in the hottest area on Earth, nowhere near here today, obviously, is about 0.1 watts per centimetre squared. Now, the light intensity, every time we press fire on the Vulcan and Gemini lasers, which are again 100 metres down the road, is 10 to the power of 18 watts per centimetre squared, which looks like that. Huge, huge number. Thousands and billions times more intense than the sunlight you feel when you're sunbathing. So anyone who's got the experimental bug behind them, you're starting to think, well, that sounds really cool. What happens when you shoot stuff with the most powerful laser in the world? And I'm an experimentalist, so yeah, I started to ask those questions too. Now, people tend to get this imagery in their head when we say, yes, we've got the most powerful laser in the world and we shoot stuff with it. I'm sorry to dampen your expectations that we certainly cannot do the kind of destruction that the Death Star can. The only thing that's really useful for you right here is this parabolic focusing lens. Because that is essentially how we focus our super powerful lasers. When they enter our target areas and enter the vacuum chambers, they are huge pancakes of light that are flying through the air. The collimated light has been expanded to a really large area. And right at the end, we reflect that light off a parabolic mirror. And the focusing is very similar to this. So that's the only kind of lifelike bit of this description. So back to reality. What happens when you do take a little piece of material, in this case it's just a piece of metal, you're now looking down with a bird's eye view into the chamber, and this is just taken with a normal camera. When we do press fire, we get this really bright flash, which you can capture with the camera, the normal SLR camera. So this is real light coming out of here. The laser's gone smack into there, created this thing, and this thing that we want to study is a laser plasma. So here comes the physics bit. This is the sciencey bit here, is a really cool bit. Because this plasma, it has extraordinary properties. So I'll just take a back step and just make sure that everyone's on the same page when I talk about plasma. And then think about it in terms of states of matter, and think about there being not 3 states of matter that we're so used to, but 4, because there's a 4th way that those particles, the nuclei and the electrons, can be arranged. And that's if we just ignore the beautiful atomic structure for a second and we blast that apart, then what we're left with is the particles themselves, but they're free of the atomic structure, atomic lattices. And instead we're left with this collection of charged particles. But we haven't taken any charge out or put any charge in, so overall it's still neutral. Charge neutrality is retained. But if you focus on certain little localized areas, you'll see that there's more electrons than ions. So overall, on the local scale, there'll be areas where you've got more positive charge and negative charge. And these things, not only is this a charged gas, but it's super, super hot. This plasma, when we fire it with the most powerful lasers in the world, can get up to millions of degrees Celsius. That's equivalent to the center of the sun, the temperature at the center of the sun. And it does so in 1/2 trillionth of a second. That's how quick our laser pulses will fire. 500 femtoseconds, 1/2 trillionth of a second. Incredibly short period of time. And plasmas, yes, it's the same thing as the plasma ball. But of course, I'm talking the temperatures that I've been talking about are quite a different realm. But the temperature and the idea of temperature and how we observe temperature, that's the same idea that we apply when we're studying plasmas. So just in the plasma ball, you see all these beautiful, pretty colours and filaments and streaks and so on. That can tell you about the energy that is being given off as the particles are heated and they cool down and they give off excess energy in these bursts of light. Well, we do the same thing in the lab, except the plasmas that we're studying, as I said, are millions of degrees Celsius and have extraordinary and exotic physics going on. And it's one of the reasons why I call this area of research the pick and mix of physics. Because whatever type of physics you're interested in, you can find it in laser plasma physics. Whether you're into fluid dynamics, the flow and the idea of turbulence and of liquids and solids and gases all combining, that's actually pretty much on the long time scales what plasmas are doing. They are flowing at very high temperatures, but there is a flow rate associated with the particles. You've got a whole heap of EM or electromagnetism going on, because you've got charged particles moving, and when charged particles move, they tend to induce themselves either electric fields or magnetic fields, and then that in turn feeds back and affects the charged particles. So you've got this incredible EM feed loop, which can get sometimes become unstable and can cause a very difficult to predict. You've got atomic physics, because of course we're breaking the atomic atoms apart. So if you want to break an atom apart and watch it jump back together again, then well, yeah, you can do that kind of plasma physics. Then there's the whole idea of radiation science, because although this is a photograph and therefore capturing visible light, the radiation that is given off by the super hot plasma is in the X-ray and gamma ray region. So actually what you're looking at here are super fast plasma jets giving off very high energy bursts of photons, bursts of light energy. And that can be applied if you're wanting to look at miniature scenarios of events that happen like this in the outer universe. So plasma jets, X-ray emission, gamma ray emission, particle jet emission, all of these things happen under extremely high temperature plasma conditions. Anything that we observe in the outer universe is existing in a plasma state. So if we generate that in the lab, we can actually start to test these laboratory astrophysics ideas. And secondly, well, if you're just into what happens when stuff gets really hot, well, we can do that really quickly and make something extreme. And here at the end is the bit that I'm interested in, so relativistic motion. How and why does a laser generate a beam of high energy photons and high energy particles? What's going on there? Well, to there, we can take another back step. This is a side-on view now. The laser is actually coming this side. This stream of visible light that you're seeing captured by the camera is actually the scattering of the laser light by ablation. So the laser is hitting a solid slab, it's just a solid slab. Laser's coming in, hitting a solid slab, and it's causing the edge or the surface of that material to fly off. It basically heats up, spits it out. So you're looking at an ablation tower here, so that's not the interesting bit. With any type of area of physics, the interesting bit tends to be the invisible stuff, the stuff that we cannot see with a box standard SLR camera, but stuff that we can see with X-ray cameras, with particle track detectors, and other types of ways of seeing particles and measuring their energy and their flux. And what we measure and what we see coming out of this is very energetic particles, extremely energetic, almost, well, in most cases, for the electrons in certainly, they are relativistic energies. And what's going on here is that the electric field in the laser pulse itself is seeing the plasma that it forms itself, and then using the interaction of charged electrons, negative particles, charged particles in an electric field, and asks what happens next. Now those that are all at that point, if there's any points clicking, pennies dropping, I'm talking about here the Lorentz force. So I'm talking simply something that you learn about in A-level science, talking about what happens when you have electric fields and charged particles and what happens when they overlap and they interact in space and time. But in this case, the electric field inside this laser is on the order of 10 to the 12 volts per meter. That, let me just tell you, after you do a trust video, that is an extremely high electric field, ridiculously high, and nothing like anything we can generate any other way on here on Earth. And that essentially, there's lots of, a couple of other tricks that happen, but essentially the laser pushes on those electrons and they can fly out relativistic energies. Now what happens next to those electrons depends on what dictates what comes out of your system, because the electrons can pull out ions and protons behind them, so you can get a heavy particle source. The electrons bashing around, wiggling, changing directions, that causes them to give off X-ray emission. And they can also interact directly with the atomic nuclei of the target, of the thing you hit, to give off gamma rays. So you've got a whole heap of really interesting beams of radiation. Now what you're looking at here is a miniature version of something that you're probably already very familiar with, the particle accelerator. And just to put that miniaturization idea in your head properly, the equivalent system or a radio frequency solid state cavity, something that does the pushing and the pulling to accelerate particles, the conventional way of doing it is using a system that's on about a meter size. And of course, you know what happens when you put things back to back and you can get to really, really high energies that we need to do fundamental physics exploration. Well, what the best one of these in the world can do in 1 meter, we can do in the width of a human hair using our miniature microplasma accelerator. So the acceleration is really miniature. And out of that, we get all the stuff that you can get out of a particle accelerator, the ones that we have on site, and ISIS and neutron, they are particle accelerators for science. We can get protons, ions, and neutrons. We can get X-rays, and we can get electrons, and we can switch those on and off depending on what you want to use. Now, this is where I started to talk about innovation and technology, because miniaturization, the moment you start to miniaturize stuff, make things smaller, you tend to increase the number of applications it can be used for. Now, this is better, this can't be better described than with the idea of computers, because way back in the day, in the 50s, this is what a 5 megabyte hard drive looked like. And this is what you would need to do, therefore, in order to take along with you 2 photos of what we generate today, or just a song file. So in the 50, 60 years since this photo was taken, there's been extreme miniaturization of computing, and therefore we are now all sitting here in this room with dual-core processors in our pockets. And computing literally rules the world. That's how the world works at the moment. So miniaturization is great for technology, and that's kind of the idea that we've got with these plasma accelerators, because they're super, super small. And so therefore we think, where else can they be used? Now, the motivation behind this is that accelerators are used more than just discovering stuff and explaining how the world works. They're used an awful lot already for things like medicine. So for years, for decades even, accelerators have been used to generate X-rays, and now they're being used to generate protons for cancer therapy. They're being used for imaging biological tissues. They're used for generating radionuclides, the things that give off X-rays and gamma rays so that we can see inside our bodies. So the question here is, can plasma accelerators be used to miniaturize the existing technology and make it more applicable, actually increase the range of these applications and be used more, even more, in a clinical environment than we are now? There's a couple of examples I've got up here of stuff that we've done in the laboratory, actually just down the road, to kind of demonstrate that. As a way of using our laser plasma accelerators to test, to see if we've got an X-ray beam that is really good. And this is one of the tests that we did at Imperial College London, was actually doing 3D imaging of a bone sample. Now this bone sample is only a couple of centimetres big, or a couple of millimeters small, so it's really quite tiny. But what this X-ray imaging is able to do is actually pick up the micro-sized features that make up the inside fabrication of what bone tissue looks like. And they were able to do this in 3D. And they were able to do this without frying the bone sample with X-rays. So actually what we have here is something that is really useful for clinicians, for the medics, because they can see the inside structure of bone. And it's also safe for the sample, so they can actually retake these samples and do whatever other clinical or medical diagnosis they do. So that was really important for them. On the radiobiology side, i.e. the cancer therapy side, there's a UK group that call themselves ASAIL, And that's a whole group of UK universities that are coming together to look at laser-driven proton and ion beams that can be used for cancer therapy. Now, the way that ion and proton beams work in cancer therapy, and any radiotherapy in fact, is to do with double strand DNA breaks. So essentially, we're using the radiation to damage the DNA structure within the cancer cells that kill it off. But with X-rays, you tend to get a lot of side effects, shall we say, in that a lot of the healthy tissue around the tumour is also irradiated with X-rays. But with protons and ions, you can really localise the deposition, i.e. you can make sure that all the damaging stuff gets to the cancer or gets to the tumour, and you minimise the irradiation and the healthy stuff around it. And just to point out how tiny these little particles are, this is a little structure of targets, one of these things that you shoot on one end of the laser. And they're working with clinicians and radiobiologists to actually take cancer cells, irradiate them with laser-driven ions, and then figure out if we've done loads of DNA breaks. Now moving on to a very different sector altogether. This is something that I just started very recently working with, actually. This is something that it's only started in the last couple of years. And that's using laser-driven X-rays. So using the X-ray beams, essentially to do imaging, X-ray imagery or X-ray radiography. But one of the really key things about laser-driven plasmas is the energy of the X-rays is so high, it's so strong that it can get through very large and very dense objects. Now, the kind of people that are interested in imaging and inspecting very large, metallic, expensive objects are people belonging to the aerospace industry. So they want to be able to image their jet engine rotating at full speed under various levels of damage. Or if you're a company that has to look after the UK's nuclear waste heap, you want to be able to look inside these barrels. So we've done a couple of demonstrations working with aerospace and with the nuclear industry to demonstrate laser-driven X-ray imaging of the inside of a fan blade. This is the titanium honeycomb structure inside one of those fan blades. And this is a miniature version, okay, it's not a full size one, I'll quickly explain there. But this is a miniature version of a uranium penny inside a concrete pot to simulate what a nuclear barrel is in real life. And essentially what they're looking for there is cracks, sign of damage, sign of failure. So anything that indicates that the inside is not stable, especially in the case of nuclear waste barrels, you certainly don't want those things to break. And in the case of fan blades, these things are very expensive. It's really not an option for any of these components to fail. So they go under a lot of interrogation and a lot of validation and inspection before any of these things, before any of the aerospace objects can be put up on a plane, and before any of these things can be stored safely, they have to be inspected. I've just got my first grant recently, our research grant recently, to develop the laser-driven X-rays more for this application. So this is something I'm working on for the next 3 years now, to actually develop the technology to see if we can do proof of concept and proof of demonstration, and to make this research really become reality. Now finally, I'll finish off with another example of the applications that we're doing. So I really like this one, because this one was something that I found quite counterintuitive at first, but is really neat. And that's in detection of security, but mainly in the idea of searching for mines underground. Now, what the idea here is a technique called X-ray radar. So it's essentially X-ray backscatter imaging. X-rays come in, they scatter off something, they bounce off something, and they come back, and then you form an image of what that thing was that they bounced off. That's been around for ages, so that's not new. Innovation doesn't always have to be a complete invention. Sometimes innovation is the bringing together of new. Innovation is sometimes the bringing together of two existing ideas, and you bring them together in a new way, and that can develop a new application. So essentially, that's what we did here. We said, if you take electrons from our laser plasma accelerator, you shoot them, they have a very short pulse structure, because the laser itself has a very short pulse duration. So this little packet of electrons comes flying through. Every time electrons fly through stuff, i.e. they interact with stuff, they give off X-rays. So So it flies through the first barrier, you get an X-ray flash, that comes back. Flies through and bashes into another barrier, you get another X-ray flash. And that comes back towards a very fast detector that can actually tell there were two flashes here, even though they're separated by billionths of a second. So extremely fast detector. And in doing that, you do that back and forth, and you can do that scanning in X. And you can start to build up pictures. This is a picture that we formed. This is our lovely picture, beautiful picture. I know it's quite pixelated, but it is the first time we've done this. So it's the first time in the world that you've seen this. But the electron beam comes in, and we model the sand as foam, and then we had a low density organic compound there to model the thing that they want to look for. Also, there's things like lead walls here, that's why you've got a really bright X-ray flash at the bottom. There's also some aluminium, it's a very soft metal, generating a bit of an X-ray flash there. And this work was with the Defence and Science Technology Laboratory, with DSTL. That's another government entity that works purely with people like the Ministry of Defence, the MOD, in order to develop technology for things like security and defence. So this is stuff that is really catching a lot of attention now and is getting really exciting. So essentially that is what I do. I do research in laser plasma accelerators, how to understand these interesting aspects, how to control them, how to make them better. But at the same time, I have an eye into the innovation. What do we want to use these for, and how can we design them to make them suitable for that purpose? And that cycle goes on and on, feeding back into itself. This is something that it's quite a unique role that I have. There aren't that many people that have this ability to do some research alongside what I would call technology transfer or technology development. But actually it works really, really well for me, and it really works really, really well for the technology I'm working at, because it's at that really interesting stage where we are starting to demonstrate for real what we can do. So it's no longer just in someone's head, a really nice idea. The vision can now be realised, and tomorrow's technology can start to be built. So, I'm finishing up now, as you can tell. Cats and balloons coming on. So, although lasers are really great for loads, already great for loads of things, including popping balloons and cats, they are incredibly important for a whole heap of different technology and applications. I just told you about plasma acceleration, but there's a whole heap of other stuff that we do in the Central Laser Facility that is really important for our future and for our well-being. As I said, this is I'm an application development scientist. If you are interested in the work I just told you about and the plasma accelerators, then this is my latest paper that was out earlier this year. It is open access, so everyone else can read it, which is good. And you can find that you can find it on my webpage, or if you, actually I should put it on my Instagram. So you're probably welcome to take it off there as well. But a final point I wanted to make as well is that with any type of innovation, it's all about the teamwork. This is a picture from the experiment I was leading last year, including my PhD student and another PhD student who's just writing up, and this is another PhD student as well. Along with, this is my boss, it's looking very contemplative there, and some other people that I work with. It's all really collaborative. I work with many people in universities across the UK, and now I'm starting to work with people across the world. And what I do is work with people, but I also tell people what I do. A big part of what I have to do is communicate to lots of people at really interesting conferences around the world in some really amazing places about what I do. So a big part of what I do in science is very much a joint and team effort. So finally, my kind of thoughts, I guess, so just to round this up in terms of how I got to where I am now and the job that I do. This is very much how I describe what I need to do now in my job role. So yeah, it's a bit of project management as well as the science research, leading and listening, communicating, negotiating, so being able to negotiate with people, especially if people clash on ideas or they clash on the way that we think we should do things, you have to negotiate there. Collaborating, translating. A lot of what I have to do is I have to be able to explain this complicated physics concept to somebody that's never heard about this idea before. I have to break it down so that I can actually bring people along with me. So I'm often working with people in engineering and people in medicine, people who haven't studied physics to the level I have for many, many years. And so you have to be able to find a middle ground. And finally, also, I think this is a big requirement of anyone who wants to be successful in a STEM career. Is key one for me is being creative, having a freedom in yourself to be creative, to think freely and to think openly sometimes, and sometimes to question your own thinking, but certainly also question the thinking of others. Dedication and confidence. Science can be hard sometimes because you're doing something new for the first time, and that can sometimes be a bit scary. So having confidence in yourself and confidence in your team is vital to keep you going, essentially. And that's what it comes down to for me. It's about using imagination and creativity to establish new knowledge, to discover new things about the world, but also to use that knowledge to build tomorrow's technology. So finally, if you are at all feeling, I know it's the end of the day as well, and a busy 2 days, if you are at all feeling like this guy, then don't be afraid by that feeling of, it can either be wow or whoa, or it can be whoa, like you're not quite sure, I don't know, I don't understand that, I don't get it. But that's the freedom of science and research, is sometimes all of us have that bit of that feeling of, I didn't really understand what that person just told me. It's okay to feel like that. That's the joy of being in science, is that you learn new things and you take on new ideas and you move forward. So embrace the feeling. So that's it from me. I am available on all of these if you want to get in touch. Please do if you want to find out any more about how I got to the job I'm at now. I said at the beginning I was an applications development scientist. You now know why I call myself that. I'm part research but part development. And it's something else I can share with you now, is that I found out this morning that my review process for promotion was successful. So I am now a senior applications development scientist. I'm going to have to update my slides from now on. But with that, I'll thank you for your attention.